Okay, so we are going to continue 7.2. So what we're going to do to just start out is we're just going to do a quick review of substitution method to take the antiderivative, and then I'm going to show you a shortcut. Okay, so first one here, we are going to let u equal natural log of x, because if we think of the top part here, this is natural log to the third. Okay, so we're going to let u equal natural log of x, which implies du is going to be 1 over x dx. So I see here I have 1 over x dx. So I'm going to rewrite this as u to the third du, which now we can integrate. This becomes u to the fourth over 4 plus c. And last, I want to rewrite this with my original natural log of x. So this will be natural log to the fourth x over 4 plus c. Just a quick note, you also can write natural log of x to the fourth power. It doesn't matter. Okay, next one. So what do we want to make u equal to? We want to make u equal to 4x squared plus 3, which will give us du is going to be 8x dx. Now, I have a 2x dx, but I don't have an 8x dx. So what I can do is I can multiply everything by a fourth out in front, and that will replace the 2x dx with 1/4 du. And then that'll just leave us with a 1 on the top, a u on the bottom. So I'm going to integrate 1 over u. So that'll be 1/4 natural log of absolute value of u plus c, which ultimately, when we go back to our original value of u, we get 1/4 natural log of 4x squared plus 3 plus c. Now, technically, we don't need the absolute value because 4x squared plus 3 is positive, but it doesn't matter to me. If you leave it in absolute value, that's fine. If you just have it in parentheses, that's fine. Okay, one more of these. So here, secant tangent, well, I know secant, the antiderivative for secant theta, tangent theta, d theta, that's secant theta plus c. So really my inside part for the u substitution is going to be theta over 2. So I'm going to let u equal theta over 2, which implies du is going to just be a half d theta. Now I don't have a half in my integrand or anywhere, so I'm going to compensate by that by replacing that with a 2. And so now I'm going to have a 2 secant u tangent u du, which will end up giving me 2 secant of u plus c. Go back to our original, which is 2 secant theta over 2 plus c. Okay, so that, again, that was a review from our previous lesson, but I want to show you there is a shortcut for substitution. Now, we can't use it all the time, but if we don't like the shortcut, you can always go back to our regular u substitution. The time that we can use it is when the derivative of u is a constant. You may apply the following. All right, so if we integrate f prime of u du, again, if u prime equals a constant, so it doesn't have a variable involved, then what we can do is just take the antiderivative divided by the derivative of u, and then we add plus c. So let me explain here. We have cosine of 2 theta d theta. So if I look at my u is 2 theta, see how u prime is just a constant. So what I can do is take the antiderivative of cosine, which would be sine, keep the inside the same, right? So antiderivative of 2 theta divided by u prime. So divided by u prime, which was 2, plus c. And that's it. So it's kind of like the opposite of the chain rule. So if you recall when we did chain rule, we'd have to multiply by the derivative of the inside. In this case, we're dividing by the derivative of the inside. Here, if we look at what would be our u would be 6x, so u prime would be 6. So antiderivative of e to a power is e to that power divided by the derivative of 6x, which is 6. Okay, same thing here. If we consider what our u is, it's 4x minus 1. So what would u prime be? It would be 4. So the antiderivative of something to the third power will be something to the fourth power over 4. But I have to also divide by another 4, which was my u prime. So I get 4x minus 1 to the fourth over 16. Now just remember, you can always check your answer by doing the derivative of my result, and I should get back the original integrand. Okay, last thing here, what we want to do is what happens when there's variables and we want to change the variables of integration. Okay, so that it just makes it when we're integrating, it simplifies our values and our integrand that we're evaluating at. So let me explain. Here, I see that I'm going to have to do a u substitution. So in this case, I'm going to let u equal my x squared minus 4, which makes my du 2x dx. Now I see I have an x and a dx, so ultimately I'm going to have to compensate for the 2 by multiplying by a half. And then I'm going to make this 1 over u du. But you see my original limits of integration were 0 and 1. I can't put 0 and 1 here because I've now changed the variable. So in this case, I want to say, all right, well, what happens when I plug in 0 for x? So take my original function, x squared minus 4. So if I plug in 0, I get negative 4. So that's my new lower limit of integration. And u of 1, so if I plug 1 in for x squared minus 4, I get 1 minus 4, which is negative 3. That means when I integrate now, I don't have to go back to anything in my original integral, okay? I now have negative 3 and negative 4 go along with u. So I have 1/2 natural log of u, absolute value of u, evaluated from negative 3 or negative 4 to negative 3. So now we get 1/2 natural log, I'm taking the absolute value of negative 3, so that'll just be 3, minus natural log, absolute value negative 4 is 4. And I know when I have a subtraction, I can just change that to natural log of 3/4. Okay, next one. This time, I want to make u equal to tangent of x, which will make du equal to secant squared x dx, which I already have in my integral. Okay, so now I'm going to have the integral of just u du. And I want to change my limits of integration. So I want to change the 0. So tangent of 0 is 0. So that one stays the same. And u of pi over 3. So tangent of pi over 3 is root 3. So I'm going to replace the top with a root 3. Okay, and now this really simplifies my problem. I can just take the integral, which is going to be u squared over 2, evaluated from 0 to root 3, which ends up just giving me root 3 squared over 2, which is 3 over 2. Because if I plug in 0, right, it's just going to be minus 0. Okay, this last one is a little bit more complicated. It uses a u substitution, but I can't use the u substitution right from the start because I can't make u equal to 9 plus x squared because then I would have to have an x in the numerator. So I want to think back to, we had a rule for 1 over 1 plus x squared dx, and that was the tangent inverse. So I have a 1 plus x squared, but if I'm looking at my original, I don't have a 1 plus x squared, I have a 9. So I want to make that into a 1, so I'm going to multiply the top and the bottom by 1/9, or you can divide the top and bottom by 9, it's the same thing. So what do we end up with? Well, we have from 0 to 3, 1/9 times 9 on the top will just give us dx, or 1 dx. In the denominator, I'll get 1 plus x squared over 9, which I can then rewrite integral from 0 to 3 of 1 over 1 plus x over 3 squared. Now I have it in the form of 1 plus something squared in the denominator. I am going to make my u equal to x cubed, which means du is equal to 1/3 dx. I'm going to compensate by putting a 3 in front, and now I have the integral of 1 plus u squared du. Or if you want to put the du in the top, it doesn't matter. Okay, let's change those limits of integration. So originally I had 0 on the bottom, but if I divide by 3, I still have 0. And what about u of 3? Well, that's going to be 3 divided by 3, which gives us 1. So we have 3 tangent inverse of u evaluated from 0 to 1. So I have 3, and then tangent inverse of 1 minus tangent inverse of 0. Where's tangent equal to 1? That's at pi over 4. Tangent inverse of 0 is 0, so I get 3 pi over 4.